Okay. Hello. Is this you? Do you hear me?
Yeah, it's good.
So it is our lecture number 4 in the computational chemistry course, and this week will be the most difficult for regarding the derivations. The rest of the course will be easier. And I also would like to announce our practical activity for the course. So everything should be pleasant. No, nothing difficult. So we should slowly start our practical part, and I suggest that if you are here on campus, we meet today at
Excuse me, Dr. Gillen.
Yes.
I think your microphone is not adjusted properly, so we are having problem hearing you.
A little louder.
You hear me? Is it better now?
Yeah.
I guess so.
Okay.
Let's see.
So we can try meeting today at 6 p.m. at Arts and Science 16B. It's a room in a basement that is equipped with right software and right hardware. And for if you are not on the campus and you do not like probably this too much of travel to go there, I will show some introductory actions what you should do at the end of the lecture, and I will also distribute the materials, kind of guide what to do and what not to do. But things are easy. I would also like to announce an option for extra credit. So this part of the course is not obligatory. You can do it, or if you find it too much difficult, you can skip it. But last year it was most pleasant and most efficient way of getting new material. So after having 2 sessions in the lab, you will try to share your experience in the form of very short presentations on some important practical steps. And I will announce suggested list of topics, but this is optional. Okay, before starting actual lecture, actual scientific material, I will review where we are now and what we want to get. In 2 words, we are splitting electrons and ions because it brings substantial numerical simplification of all problems. But we are trying to do this process slowly, carefully, step by step. So here, a little human factor to our boring lectures. Here, the person who wrote a book I was distributing a week ago. And I've learned about this. The book is really good. It stands out of standard textbooks. It is more research, but at the very beginning, he gives very nice introduction to key points of the computational chemistry. And I've learned him because in year 2000, he was my member of the degree committee. Okay, so it is not yet a start of a lecture. It is still a general advertisement. So please sit in a relaxed way. I give you a warning when you should concentrate and percept important material. So couple of additional words about practical part. So what we can try doing in the computer lab and what you could report here as a short presentations for next lecture. So those all are like very simple alphabetical things. So the one is what is Linux, what is the language one talks to supercomputer. Another is what is a concept of job, like giving orders to bigger supercomputer. And then there is a software that allows one of many brands of software that allow to build atomistic models just by clicking and drawing. Another thing that we should learn sooner or later that there are different formats of saving this information, and it is a very simple practical skill to convert between different formats of files. So there is no science in it, but it is important practice. And there are also ways to visualize atomic models, and there is a software that allows to convert X-ray diffraction data into the information that is fed into computational calculations. Okay, please keep relaxing. It is a review of what we did on previous lectures. So we agreed that there is some red box that allows to convert atomic models into observables that can be compared to experiment. And we started to build an account for all features of molecules, starting with positions of each ion, specifying charge, interatomic distances, and building contributions to energy. Contributions to operator of energy that are needed for precise quantum treatment of a molecule. So before we give orders to computer, before we use software packages with some theories, we coming this simple way in getting and percepting basic concepts that are used in the software. So since we are speaking on a quantum language, we are building a Schrödinger equation for electrons and ions. And what we did on previous lectures, we were proposing a wish to split everything that relates to electrons and everything that relates to ions into a separate set of equations. And it would be really great if you could do so. But this is a hard task, and we are trying to reach this goal step by step. So as a first ladder, we reshuffle the terms in the Hamiltonian that are related to ions and related to electrons. And then we considered only the part that relates to electrons to build a basis to set up some set of functions that are used later. And as our main achievement before the weekend, we agreed that one can look for a wave function of the whole molecule, everything, electrons and ions, as a superposition, as a sum of these atomic, these electronic functions that come from electronic part with some unknown coefficient. Okay, I think we are done with the review, and I'm going to start some new material. So this is a difficult procedure, both intellectually and, well, it is not super difficult mathematically, but many textbooks just skip it. They tell that the final result that one can consider electrons and ions separately under certain approximation. But as time passes by and theory develops, one recovers that many important processes are connected to the events when electrons and ions are not separated, and we should be very well educated in understanding when we can separate them and when we cannot. So it is a little motivation to spend time on lectures. So what we are doing, we are taking the molecular Schrödinger equation for the whole molecule, and we take the expansion, the shape of solution, the expected shape of solution. Then we plug it into there and see which consequence we are doing. So the rest of the lecture, the rest of the hour, we will be just doing this and following, analyzing what we are getting. If you got this idea, you can stand up and do. So in substituting this form of solution into this equation, we are going to eliminate anything that relates to electrons, because we already have some equation for electrons. This one is pretty good to describe electrons. And now we need to treat ions that do not have any electrons, or have maybe some additional term that describes the behavior of electrons in average or in some fancy way. And therefore, here are some steps. We are going to eliminate electronic operators, then we eliminate electronic wave function, and then there are some other technical steps that we are going to use the property of orthogonality of electronic wave function, and finally we will not finish everything today, but we will understand after a few mathematical derivations that the key feature of the connection between electrons and ions is kinetic energy of ions. Okay. So before we go to the next slide, you see here is the molecular Schrödinger equation. We put it as an eigenvalue equation with 4 terms. 3 operators on the left part and 1 eigenvalue on the right part. What we are going to do to be able to speak about each of them, we will open these brackets and write this equation into form of each term per line. So there is nothing new. I'm just repeating the same equation as on the last page. So we are going to plug in the total molecular wave function into here in place of this dot. Summation over all electronic states. This expansion coefficient must depend on position of ions times. Electronic function that depends on position of electrons and position of ions. And now I'm going to practice calligraphy and just repeat same expression again and again. You can do it in your notebooks, or you can skip this silly operation. Okay. Well, let's just look on this equation and think, are we happy with it and what it is, what we do have here. So these three terms are operators. The first two operators relate to ions, and the third operator relates to electrons. And this one is just a number. So we are, yes? Number in a mean that multiplying this number by a wave function, you do not change the shape of the wave function. Dimension of this number is energy, eigenenergy of the whole molecule or state of the molecule. But yes.
Excuse me, Dr. Kelly.
Yes.
Can you pull your microphone a little closer to your mouth? We have a hearing
Oh,
problem.
sure, no problem. Is it a little better?
Yeah, it's better, I guess.
Okay.
Yeah.
So you had a question or just suggestion of putting?
No, just for hearing problem. We have here.
Okay. So if we want to speak about ions only, we need to look through this equation and try a way to get rid of this operator and each of these electronic wave functions. We do not know how, but we will do it sooner or later. And in order to eliminate electronic operator, we can use a very specific property. Let me go to the next slide, where I think we have same expression, just arranged in a typed way. So if you are looking on this term that has electronic operator, we can recall that acting by this electronic operator that you were describing as pseudo-electronic or fake electronic operator because it has some parametric dependence on position of ions. If we act with this operator onto electronic wave function, we are getting some electronic eigenenergy and wave function back. And here the H is operator in respect to electronic space, and this is a number in the sense that it is eigenvalue. It is a number, which means that it is not an operator. And if we plug in this eigenvalue property into the third term, we will see that we can replace our operator of energy with eigenvalue of energy. Well, we should put it here under the sum sign, but it is a little small positive help in our big goal. We are getting rid of electronic operators. We are going to eliminate electronic operator. This one. Okay. So here is what I already have written. And if we plug it in here, then we remove operator here and we add eigenenergy. Is okay. Here we have W. Okay, so we are done with eliminating electronic operator. Now we do have these electronic wave functions across the equation. We are going to do something to get rid of them. in order to complete this little task, we need to make an additional assumption. So we were not solving this electronic Schrödinger equation. We just decided that someone can solve it for us, and we are going to use this electronic wave function as a basis. Now we can assume that this basis is good, is comfortable to work with. And one of the properties that we are going to assume in this respect, that those electronic wave functions are orthogonal to each other. Orthogonal and normalized. So if you take one electronic wave function with index A and another electronic wave function with index B, and we integrate them over all electronic variables, we will get either 1 if A equals B and 0 if A is not equal to B. So it is like Kronecker delta symbol. It is either 1 or 0. There is no big science in it, but it is very comfortable assumption, and set of functions can be transformed if it is a full set of full basis. It can be always transformed to orthogonal set of functions. And if we use this property of orthogonality, then we can do something really simple and helpful. We just take the left part of this expression, the E integration and wave function conjugate, and multiply it to each term of our molecular Schrödinger equation. So the idea is, if we perform the integration, then the wave functions with index A and with index B will convert, and instead of wave functions, we will have just numbers, which can be either 1 or 0. Hopefully, we'll see if it will work. So by using the property of orthogonality, we are going to eliminate electronic wave function. Hopefully, we will approach closer to getting things important for describing of ions. Yeah, probably writing by hand is much better than putting it there. So we do have several terms. We multiply each term from the left by this prerequisite for eliminating electronic wave functions, and then we have four terms, and each term has 3 factors. So it has the orthogonalization part, it has the original operator, maybe some summation, and then on the right it has electronic wave functions that we are going to eliminate. So each of terms follows the pattern of 3 factors. And our 4 terms, just refreshing my own memory, are kinetic energy of ions, Coulomb interaction between ions, then eigenenergy of electronic part, and then eigenenergy of the whole molecule, this molecular eigenenergy. And for each term, we are doing the integration. So if we do integration for 4th term, for number eigenvalue, and for third term, which is also number and eigenvalue, the integration is not affected by presence of a number in between of this expression. 2, 3, and 4. Integration is straightforward. For term number 2, we do have operator of ions interacting with each other. But this operator has a diagonal form, and it depends only on position of ions, so it is not perturb the presence of this operator, which is diagonal in respect to ions, doesn't change our operation of finding matrix element of the using the orthogonality property. So we will also get a delta function. Yeah, here is the same thing in an ugly way. Functions, operators, and integration. And the only important term that the integration is difficult to perform is term number 1. Let's see if there is a so our kinetic energy of ions is square of momentum of ion over the mass of ion, and there is also information. And the momentum operator is a derivative over the position of an ion. And this derivative of position of an ion is something that can act on the electronic function that depends on both electronic and ionic position. And this operation, or momentum squared, even stronger, this will affect the basis wave function. This will affect this electronic wave function and change the result of all integration in the first term. So in all but first, we will easily get delta function as we originally decided. So we get rid of operators, and we get electronic wave functions, and we get numbers. For the first term, we need to commit additional effort. We cannot put this wave function and this wave function together. We need to act by kinetic energy operator first. And this will make some changes. Kinetic operator is derivative, and therefore first term is important and cannot be done in a simple way. So here's the same thing, just in this ugly diagrams. So for fourth, third, and second term, we just have this integration. They are not affected by whatever we have on the right side, and we can replace them by delta function. And for the upper term, for the first term, we should keep the expression for separate treatment and for detailed analysis. Okay, so here we put delta functions instead of these integrals. This term with we do have a summation delta function and some coefficient, right? And typically the summation sign times delta function, they eat each other and they select out of whole range of coefficients only one coefficient with a selected index. Select only one coefficient. So instead of these terms, we will simply have high E, high E, high. And for the first term, we still have something more complicated. And for kinetic term, for the first term that is not simple, we should realize that we have an operator of momentum squared and realizing that each p operator is a derivative, we should look on the second derivative of the electronic wave function. Here instead of r, it's a r, and if we open this expression, we will see several terms that do contribute to the first term, and some of those terms are big. Some of them are contributing to the kinetic energy of ions all the time, and some of them are small if ions are not, in some cases, they're not big. So we can try doing it now, or we can postpone it for later. Our effort a little bit easier. It really takes much longer to prepare than to pronounce. So let me summarize where we are right now, and we will finish this separation of ions and electrons probably next time. And now in the remaining time, I will just start talking a little bit more about practical side of this course. So we are trying to separate electrons and ions, and we already have an equation for electrons. But in the overall molecular Schrödinger equation, we do have a term for kinetic energy of ion. And we will see later that it has term that corresponds to pure just energy of ions moving, and there is an additional term that arises because electrons jump between different orbitals. And this second term can be either assumed small, and then it is done in 99.9% of computational chemistry, or if one is looking to electron transfer, optical, non-radiative processes, emission from probe experiments, then probably one can look closer onto this term. So what we should do in our next segment of theoretical consideration, we should slowly, carefully analyze kinetic energy of ions and separate this pure term and mixed term. And then we will go through definition of potential energy surfaces and non-adiabatic couplings, and at the end we will have two separate sets of equations for electrons and for ions. So as an announcement, I can briefly show you how the final result looks like. So after finishing our next theoretical segment of the course, we will see this part, which is electronic equation for that we were already discussing. So kinetic energy of electrons interacting with each other, and electron-ion interaction, and there will be Schrödinger equation for ions that will have this high coefficient with the meaning of wave function of ions, and it will has the pure kinetic energy of ions and the rest of terms that we were talking about. But there we are going to neglect everything that looks strange, everything that goes apart from pure kinetic energy, and we will discuss when it is possible to do. Here is our general form of solution that we started from. And here is the with four lines equations that we were treating today. Trying to discuss. Okay. Did you see the Dropbox that I have opened for the homework? You can submit it there. Okay, then we can establish our. You didn't? I did it maybe late during the night, last night. So please check and report me if you do not see it. And homeworks are not significant part of the course. They're just to entertain you and me. But it is good if you have a way to communicate information through this Dropbox rather than email. So if any of you are really busy, you can go. If you have a little time, I can informally speak a little bit more about our practical side, and especially for SDSU part of our course, to just show what we will start doing tonight in the lab.
So how will we do here? Like lab?
Well, the whole practical part can be arranged as installing specific software on your laptops,
Okay.
connecting to our supercomputer, and then if you have some and following suggestions that I will distribute. And if you have any difficulties, just send me a short email and I can log into the same directory where you are working and give suggestions what is right or wrong.
Okay.
This should work. We should
Okay.
arrange this.
So how we install it? You will provide?
I'm going to start talking about it right now.
Okay. Sounds good.
This is there is a free software which is really helpful. So in case we are very successful with our practical part, in case every one of you is volunteering to make little presentations, we do have a list of subjects and we have a list of attendees. And please correct me if I have some names wrongly. And what we are going to do is to make connections between subjects and people and decide who want to present what. Here my lines are arbitrarily. if you really want to deliver some specific subject, you're welcome to be first. Send me an email. I want this. Like, if, huh? Send me an email for just for the record. For I'm really flexible with whatever you choose, but for your own benefit, you may want to select something that you do not know. Okay, so I'm going to start going across the subjects in my way, but then after you practice it, you can build your own little presentations, and if you like, of course, and share your experience when you get it. Okay, so this is most important slide for SDSU. So there is a piece of software that is called Sigwin that helps to connect to any other server or supercomputer and operate it as if you were present here. And this software is for PC, Windows machines. For other platforms, there are some other software, but I think the PC with Windows is most popular. So you simply go to website of the software and download it. So just find where you have a install buttons, and it should be very self-explanatory. If there are some little, the only strange part that it prompts you to tell where you want to download the source, because there are several mirror sites across the world, and you can navigate the mirror that is closest to us. Probably in Argonne or somewhere you will recognize by names. But if you click any of them, it will work same speed, maybe like 10% of the speed will be different. If you care about 19 seconds instead of 20, then you can spend time on selecting where to download it from. Yeah. It is a website. You click Setup. And after you get into this software, after you install it, you can run it on your PC. So it will look as a box where one sees an option to type something. So the whole procedure is talking to computer. You type some command, and computer responds at once, or no, I cannot. And before we go forward, I probably can make a little illustration. So I'm going to close this PowerPoint for a second and try opening it right here. So there is this Sigwin already installed, and it took me maybe 4 minutes after our last meeting. And then you have this window where you can type commands. And the most important command is SSH. Do you see what is on the screen, or it is too small? Okay. Then probably I'll just show that it works, and then I go back to PowerPoint where I have enlarged all fragments. So there are the main command number 1 is to connect to supercomputer, and to do so one needs to one needs 3 baby steps. First, tell the command to connect SSH. Second, give the username, which is either our common name for the whole group or your personal name if you have account on a supercomputer, and then hit enter. And between name and of the user and name of the computer, you put the ampersand symbol, same as one uses in the email. It shouldn't be difficult. And then you type a password, and you are in. So right now, I'm inside the supercomputer. So here is the name of the supercomputer. Here is the common name that you can use to connect them. And here is the old password that I'm going to change in a day or two, and will communicate your new password privately. Because system manager, is there difficulty with PowerPoint? I do not see PowerPoint on our screen.
Yeah, display is gone.
Okay, so I'll just keep talking what we are doing. So, okay. Would they still hear me, or the sound will disappear?
We can hear you.
Okay.
God. It's gone. Everything. Everything's gone. कति धेरै ठुलो हो यार यो यस्तो पनि हुन्छ यसरी के पढ्दैछ टेन क्रेडिट खेर जान्छ त्यति क्रेडिट खेरै भयो सिक्यो भने के गर्नु यतापट्टिको अल्छा गइराखेको छ
Okay. Is this you? Do you? Okay. Do you see it? Do you see the screen?
We can hear you, but we cannot see you.
Do you see the slides?
No, nothing.
Okay. So then I probably will be quick, just giving some verbal description. But at the end of our meeting, I will send you the slides.
Okay.
If any of you have access to D2L, it is already there.
We don't have access to D2L.
Okay, for those who do not have D2L access, I will just send it as an email.
Sure.
Please remind me if you do not see it in
Sure.
next whatever 20 minutes. So after you log in, there are several commands that one should try and one should feel comfortable with. There are commands to browse through directories, same as in Windows computer. You click on the folder, open it, and click on the next folder. Instead of this clicking on the folders, there is a specific typed commands that you type to the computer. So they are cd for change directory, they are pwd for pathway detection, detect which directory you are at. And there is a command that you just type make mkdir.
Excuse me, Dr. Kim.
Yes?
I have problem going into the supercomputer. Can you repeat the command? This SSH command,
Uh,
the first
you
one.
should try SSH
Yeah.
empty space.
Okay.
Then you type my last name,
Okay.
all lowercase, minus
Yeah.
lab, L-A-B,
Yeah.
then symbol at
At the rate
HPC,
spc.ust.edu.
yes, USD.
But
And then it
your
will
last
ask
name
you, it will ask you,
Kilin, right?
yes.
But it says like, I'm not sure why it's bad command. Command not found. SSH command not found.
Okay. I have an idea what is going on.
Okay.
Is it interesting for everyone right now, or we should probably do it in the lab? I can quickly answer this question, and then we probably should complete our meeting, because answering on the questions is a little bit different thing than lecture. Okay. 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 Let's meet today at 6 then. And for SDSU,
Yeah.
send me an email, and I have an answer for your question.
Okay.
Just it should be interesting for everyone in the audience.
Okay.
Okay. Well, we'll continue next time our theoretical session, and at the end of the meeting, I will give a little more slides. But after our meeting in the lab, you will be able to do magic. You probably will not need all the slides. Okay, thank you for coming, and class is dismissed for today. Ask someone else. It is arts and science. It is not lab library.